Okay, in this video we're going to talk about function transformations. So what we're looking at is a parent function, and that could be really anything at all, but a parent function is like the simplest form of that type of function. So what I mean by that is if you have something like y equals the absolute value of x, right? I don't have anything inside with the x. I don't have anything on the outside. It's just simply the absolute value of x. Some other parent functions that you may see are like y equals x squared. Right? I don't have, it's a parabola, but it's like the simplest form of that I can get, x squared. I don't have x squared plus anything else or minus anything, multiplied by anything. It's just y equals x squared. Okay, and you're going to see a lot of these, like maybe even like e to the x, an exponential function. You may see a trig function, which is what we'll look at later on, y equals the sine of x. But all of those things would be considered parent functions. And what you're doing when you do function transformations is you're taking that parent function and you are doing some addition or subtraction or multiplication to that thing to change the way the graph looks. Okay? So for the sake of these notes, I need to be very clear on this. Just for the sake of these notes, I am looking at the parent function y equals the absolute value of x. I'm not gonna do any examples with any other kind of parent function. Okay, I could do a ton of parent functions here, but I'm going to look specifically at y equals the absolute value of x, and I want you to realize that y equals the absolute value of x is a v, if I graph it, that has a slope of 1 going in each direction. Okay, that's y equals the absolute value of x. So if you look through these notes, look, every single time I have that thing graphed. Every single time, this is the absolute value of x. Every single time, y equals the absolute value of x. And I'm going to talk about how we can start to move these things, shift them and stretch them out and reflect them and things like that. Okay, so what do we do to that specific function to make that happen? So if I want to take something and vertically shift it, what I'm going to do is add on the outside of the function. So this is essentially to take f of x and then add or subtract some value. Okay. If I add that value, so what I'm going to look at is absolute value of x. So if I did y equals the absolute value of x and then I add some number c to it, that can be anything at all. I'm just going to say plus c. What that's going to do is it's going to take this graph and it's going to move it up. Okay, it's just shifting the whole thing up c units, whatever that is. So if I move it up 2, that'd be plus 2, or if I plus 3, I'd move it up 3, whatever. Okay. If I take that function and I subtract a c value on the outside from it, then that's taking that thing down c units, and I'm going to get that exact same graph just shifted down. Okay, so that's how you shift up and down. If we want to shift it from side to side, then we take the function f of x, but on the inside we are going to add or subtract that number. So how does that look with absolute value? With absolute value, we're going to look at y equals the absolute value of x plus c, and y equals the absolute value of x minus c. So if I add on the inside, what that actually does is it takes it left c units. So I'd move it just to the left. Now I get that exact same graph as I go to the left. So that's just going to be whatever c units is to the left if we add. If we subtract c units, that takes it to the right. And that's going to move it this way, c units. So if something happens on the inside of the function, it typically does the opposite of what you may naturally think it would do. You probably would think that adding would move it to the right, when in fact it actually moves it to the left. And subtracting moves it to the right. Now on the outside it worked the way that we thought it would, and that's always true. So adding is going to move it up, subtraction moves it down, but on the inside it's kind of opposite of what you would think. Okay, reflections. If we reflect something over the x-axis, so I'm going to do x-axis first. If I reflect it over the x-axis, what I do is I take the function and I make the whole thing negative. So this is going to be negative f of x. So for absolute value, what that means is I'm going to do a negative on the outside I'm going to do negative the absolute value of x. What that does is it reflects this entirely over the x-axis. Okay, and we get a absolute value v that goes down. If we want to reflect it over the y-axis, then we actually do f of negative x. And what that means with absolute value is I would do y equals the absolute value of negative x. And the negative's on the inside. Now, if you reflect the absolute value graph over the y-axis, like this piece on the left becomes the piece on the right, and the piece on the right becomes the piece on the left. So I get the exact same graph. Right? If I reflect it over the y-axis, I get the exact same thing. And this should kind of make sense for absolute value functions, because if I plug in 2 or negative 2, and I take the absolute value, I get 2, right? So if I just make everything on the inside negative, when I take the absolute value, it changes it back to the positive of that, and I get those same values over and over and over again. So a reflection over the y-axis in this case doesn't change my graph, but that's how that looks. Negative on the inside. So negative on the outside, reflection over x. Negative on the inside, reflection over the y. And then lastly, we have some stretches and compressions, both vertical and horizontal. If you want to stretch it or compress it vertically, what you do is you multiply on the outside of the function. So if I had y equals c times the absolute value of x, and in this case I'm going to talk about c being greater than 1. Okay, if c is greater than 1, I'm multiplied by something greater than 1, then what happens is it's going to vertically stretch this out. So what I mean by that is, let's say that c is 2. Every y value is going to become double what it was before. So don't just go up 1. So what I'm saying here is, like, this y value is 1, it now becomes 2. This y value is 2, it's now going to be 4. Or this one's 3, it's now going to be 6. And what's happening is we are taking this thing and stretching it out vertically, so it's going to appear taller and skinnier than the original one. Okay? Now, same exact thing if I multiply on the outside, but if your c value is between 0 and 1, so if we have some kind of fraction up there, y equals 1/2 x, absolute value of x, or y equals 1/10 the absolute value of x. What that's actually doing is taking this thing and vertically kind of squashing it down, right? So think about something on top and bottom of this graph, and it's just like squeezing it down and flattening it out. That is what that happens if that c value is between 0 and 1, some fraction there. That is a vertical compression. Okay, and then as we've talked about before, if something happens on the inside, it's kind of the opposite of what you would think. So if I do a multiplication on the inside and that thing is greater than 1, so if I looked at y equals the absolute value of cx and c is greater than 1, it doesn't stretch it horizontally. Okay, it's going to shrink it horizontally. Inside happens the opposite of what you would think. So what this is doing is your y values are actually staying the same, and your x values are becoming half of what they were before. So those 2 points I just made, I'm looking at x value 2 gives me 2. Well, now an x value of 1 will give me 2. Or an x value of 4 would give me 4. Now an x value of 2 would give me 4, right? So it's taking this thing and it's horizontally compressing it in, right? Squeezing it from the inside, from the outside, squeezing it towards the inside is what we've got going on there. And then again, same thing if I have a multiplication on the inside. If the c value is between 0 and 1, then this is going to horizontally stretch it out, which is essentially doing, it's doing what with the absolute value function. It's horizontal stretch is the same as a vertical compression, and a horizontal compression is the same as a vertical stretch. That's not always true, but you can see that from these graphs that stretching something horizontally with this looks the same as compressing it vertically. okay, and vice versa. All right, so again, I want to be very clear. These examples are just with absolute value functions. We're going to take these transformations and we're going to apply them to all different types of functions. And I'm going to show you this sheet really quickly. What I've done here is I've taken these different parent functions. So x cubed, 1 over x, square root of x, absolute value of x, that's the one we just did, natural log of x. All of those are parent functions. And what I'm showing you is the vertical stuff happens on the outside. So if I want to move it up or down or reflect it over the x-axis, right, or reflection over the x-axis affects a graph vertically. Or if I want to vertically stretch or compress, all of those things happen on the outside of the function. X cubed plus c, or x cubed minus c, negative x cubed. Like all of that stuff happens on the outside of the function. But if I'm going to move it horizontally, or shift it, or translate it in any way horizontally, then that happens on the inside. So if I want to move it left, or right, or reflect over the y-axis, that's going to change the thing horizontally. Notice all those things happen inside the function. I have to do those things to x before I cube it. Notice the cube is on the outside every single time. I've got to do those transformations and then put it into the function. So reference this sheet. I have it attached into this document, but reference this because it is helpful when it comes to, does it need to happen on the inside or the outside, and what does that look like given the function that you have? What does the outside look like? What does the inside look like? Okay. Function transformations, they're important. They don't go away. You use these ideas a lot moving forward.